So it's a pleasure to have Dr. Derya Aksaray today as our speaker for ROMER Talks. She is an assistant professor in the Department of Electrical and Computer Engineering at Northeastern University, and she's a core member of Institute for Experiential Robotics, which is directed by I'm sorry. Ashkin Pader, right? Okay.
Mm-hmm.
And previously she was an assistant professor in the Department of Aerospace Engineering and Mechanics at the University of Minnesota from 2018 to 22. She also held postdoc researcher positions at MIT and Boston University. She received her PhD degree in aerospace engineering from Georgia Tech and her BS in aerospace engineering from METU. Her research interests lie primarily in the areas of control theory, formal methods, and machine learning with applications to autonomous systems and aerial robotics. Without further ado, I would like to leave the stage to her and thank her again, for basically sharing her research with us.
Thank you. First of all, thank you very much for inviting me to this seminar series. It's really a great pleasure to give this talk today. So my talk will be about reinforcement learning for dynamical systems with temporal logic specifications. So some of you might have already have some familiarity, but reinforcement learning is a very popular approach for autonomous robots or decision-making agents to discover an optimal behavior through trial and error interactions with the environment. And if you just Google reinforcement learning, a standard picture will be this one, where you have the decision-making agent. It interacts with the environment by choosing some actions. And after taking these actions, as you can imagine, its state will change and it will receive some reward. So the environment will respond as the next state and reward. And based on this information, the agent can actually change how to make decisions for the next actions. And this type of techniques are used very frequently in order to learn, for example, some skills like grasping an object or walking. In games, for example, in order to learn the winning strategy, again, reinforcement learning is frequently used. And in addition to them, for autonomous systems, in order to learn the trajectories, like the optimal trajectories, again, there are ways that you can formulate reinforcement learning problems. So the key idea here in reinforcement learning is the designer of the task needs to provide a feedback to the decision-making agent in terms of a scalar function. And what I mean by that is, think about a drone, and as this drone, we would like it to achieve a surveillance task. And the task is monitoring this yellow region as long as possible, but in the meantime, avoiding flying over this red region. So as the task designer, we can actually assign a very positive reward to the yellow region and a negative reward to the red region. And let's say the other states have 0 reward. And then as the agent moves in this environment, if, for example, it enters a state which is in the yellow region, it will get a positive reward, meaning that it will tend to take the actions that will take it to the yellow region again in the future. And similarly, if it, for example, visits a state in the red region, because of getting a negative reward, this will be a negative reinforcement to the system. So next time, when it is in that state, it will not tend to take an action that can likely to take it to the red region. So based on these trial and errors, the agent can mainly learn about staying in this yellow region as long as possible. Now, the formulation of reinforcement learning starts with first designing the decision-making agent as a Markov decision process. So a Markov decision process is a tuple that contains a discretized state space. So even if our robot is operating in a continuous space, there's always a way to discretize the state space. For example, in this picture, you can see that I can create my state space as a grid environment. And then if my robot is in any point in this grid, I can say that it's in the sigma 1 state. And in order to represent all of these states, let's say we are also considering the centroid of that partition. So all the states, all the discrete states here will constitute the discretized state space of the environment. And then the agent will have some actions. And those actions are the maneuvers this can take. In this representation, for example, if the agent is in sigma 1 state, there might be 4 feasible actions. It can take up, this diagonal action, right action, and then the staying action. So there are like these finite number of actions in the action set. And in MDPs, another thing is that when the agent takes a transition, for example, going from one state to another, there might be some stochasticity. So the stochasticity can be internal, for example, because of the actuations. The agent wants to go to up, but because of maybe some failures or actuation uncertainty, most of the time it goes to up, but there's a slight probability that maybe it just stays in its current state. Or there might be environmental uncertainties. If there is a gust, even if you want to go up, there might be a possibility that you can go to one of the adjacent cells. So this is the stochasticity in the state transitions, which is described as this P function. And then there would be a reward function that is assigned to each of these states, or state action pairs. So this means that when the system takes an action and finds itself in another state, there's the reward that is revealed. And this is the reward that I'm going to link it to the reinforcement learning problem. And then when we say a control policy pi is mainly a mapping from the state space to the action space. What it means is that wherever the agent is, by looking at the pi, it can actually tell it which action it needs to take. And this MDP problem is used very, very frequently, not for reinforcement learning, but in order to find optimal control policy. So this is a very general representation. But in the case of machine learning, like in the canonical problem, we consider an MDP and we don't know the transition probabilities. So suppose that the system behaves in a stochastic fashion, but we don't actually know this P function. And the goal becomes, how can we learn a policy which maximizes the expected sum of rewards? So if we don't have the explicit representation of this P probability, it would be really hard to compute what will happen after taking an action, because you don't know how the agent will behave. So that is the reason why the trial and error becomes really critical in the reinforcement learning part. And if you look at the literature, there are a lot of reinforcement learning algorithms. For example, they can be categorized as model-based and model-free. For example, in the case of model-free, we don't want to learn the model. You can directly update the value function or the policy function so that you can, by observing these rewards, you can update the value or the policy directly. But in the case of model-based, you don't know initially the model, but through the empirical observations, first you build the model, and then by using this model, you can find the optimal policy. So as I said, there are various types of RL algorithms. The one that I'm going to use in my research is the Q-learning algorithm, but the things that I'm going to describe may not necessarily be used only with Q-learning, but Q-learning is again, very widely used algorithm. This is a value-based algorithm, model-free, meaning that we don't need to know the model. And once you observe the reward, you can directly update the value. And based on that, we can say something about the action selections. And the main mechanism is, let's say our agent is at state S, and then it takes an action A. And after taking this action, it will find itself in the next state, let's say S prime. And then there, it's going to see a reward, which is the R. And then it needs to update the Q function. So there is this Q function, which is a value function for state action pair. And then this is mainly updated as a weighted average of the previous Q value and the things that is seen by the reward. So if you carefully look at that, we consider the previous Q function plus the current reward and the potentially maximum receivable future reward that could be taken after S prime. So this is the way that you can update the Q function. And in the literature, this is very powerful because there are theoretical guarantees, meaning that if this update is continuously done, then you can have the convergence guarantee. So this Q function will converge to the optimal Q function. And this is very important because once you can find the optimal Q function, the optimal policy pi star would mainly be the action that is maximizing the Q star value. So for that reason, I choose Q learning because of its theoretical guarantees. And as you see, it has a really simple mechanism. So you only need to, once you observe the reward, you only need to update the Q function. Now, what is the motivation in my work? In the title, I said that I am going to talk about reinforcement learning, but with temporal logic specifications. So this time, I just want to say that, let's say I don't have a task which is like go somewhere and stay there as long as possible. But let's say I have a task which is first go to A and then go to B. So I just put an implication formula. I need to achieve something first, and after that, not implication formula, sorry, I just give like some ordering. So first do this and then do this. So in that case, if we think about it, how are we going to, for example, design the reward? Then in order to create incentive to the agent to first go to region A, in a similar manner, we can say that, okay, I can have positive reward for region A, and I will put negative reward to region B because I am trying to make the agent to learn first going to region A. But once region A is visited, then I have to change the rewards. This time I have to make region B needs to be positive, and then region A needs to be negative so that it can learn going to the region B. So as you can imagine, if we increase the complexity of the task, then we might need some time varying rewards. But if we think about the standard literature for reinforcement learning, they can only work with sum of static rewards. So let's say some rewards are spreaded in the environment, and you can maximize, as you see in this function, the expected sum of reward. But here, like I motivated that in the case of more complex tasks, there would need a more, there would need a time varying tasks. So the main question here is, how do we design rewards to ensure learning of the complex tasks? And here, the motivation of temporal logics comes. So temporal logics are specification languages. And instead of using, for example, algebraic functions, you can use these Boolean temporal operators to rigorously write very complex specifications. I have a few examples in the following slides, but in the literature, linear temporal logic, for example, this is used very frequently. This is the propositional logic with no explicit physical parameters, meaning that you can describe things like eventually go to A, but you cannot describe eventually in 10 minutes go to A. There's also another language, which is called signal temporal logic. This time you can describe things like eventually go to A, but in addition to that, you can also say, like put functions inside of this formula. And again, I will have some examples for STL language. And if you look at the temporal logic literature, so if everything is known, again, think about the Markov decision process representation. If we know the transition probabilities, rewards, and everything, and let's say there is a specification, that you want to achieve, there are techniques that you can find the optimal policy. But the question is, if the dynamical model is unknown and there's an objective as a temporal logic formula, then how does the agent learn an optimal policy in the case of these unknownness? And this is indeed the objective of my research. So I am going to consider a system with unknown transition probabilities. And then in terms of objective, I will not consider a standard sum of reward, but the objective would be an STL specification, which can express a very rich and complex behavior. And then I'm going to show how to formulate a learning problem with formal guarantees, like satisfying this STL formula. And with that, I will just introduce signal temporal logic and give some examples about that. So as I said, this is a specification language, and this can even like describe continuous time series, like the behaviors of that. And for example, this G013 as smaller than 6 is a formula, meaning that I want my signal to be always below 6 within a time frame of 0 to 13. And if you look at this picture, let's say I have this S1 signal and the threshold 6 is here and time is 0, 13. So if my signal stays inside of the shaded area, this means that this signal satisfies this formula. We can also describe more complex specs. For example, this one is eventually globally. So I use 2 recursive temporal operators. And then based on these inequalities, you can also describe specific areas. So this means that there exists a time t between 0 to 12. So this would be this part, such that the signal settles between 3.5 and 4.5. So this describes this portion within t to t plus 2. So can you find me a time instant where in the following 2 seconds or 2 time steps, the signal will settle down in this desired region? And if you look at this signal, whether or not it satisfies this specification, there are ways of finding it out. But you can see that indeed there is a time instant, which is 11, which is in between 0 to 12, such that in the following 2 time step, the signal is inside of this region, like in this like shaded region. And if I change, for example, the order of these temporal operators, previously it was FG, so it is eventually globally, but this time it's globally eventually. Then these type of specs can describe periodic behavior. So this is mainly showing visit regions A and B in every 3 minutes along a mission horizon of 10 minutes. And which means that this time I have a 3 time step shaded area, as you see here. And I want the signal to go to A and B in that like shaded area. But I'm also like shifting the shaded area. So whenever I shift, I have to make sure that the signals, one portion would be in A and another portion would be in B. And if we do that, again, this signal satisfies this specification. So one very powerful thing and different thing of STL from the other specification languages is it has a notion called robustness degree or degree of satisfaction. For example, in other languages, one can say something about in a binary fashion, whether you satisfy it or not satisfy it. But with STL, we can actually quantify how good the system or the trajectory satisfies the formula. So this is called the robustness degree. And if robustness degree is negative, it means that it's a violation. If it is positive, it means the satisfaction. But if it's the positive large number, it means that under a disturbance, it's less likely to violate the specification. So it will continue to be a satisfaction. Or if it's a very large negative value, it means that it's very hard to fix that constraint. So it really strongly violates the specification. So in a way, you can quantify this degree of satisfaction thing. And the way it's computed is through these min and max functions. So recursively, you use min and max functions. And again, just an example. So let's say we have a signal like this. And then this specification means that for all t between this time window from 0 to 7, I want the signal's element at each time step greater than 1. And if we look at this, it's indeed a satisfaction because visually we can say that every point is above 1. But if you want to calculate the robustness degree, what we do is we are actually looking at the signal and find out the minimum distance to the boundary, which is actually this point. And this says that if I perturb this trajectory, let's say 0.5 amount, if this is, for example, 1.5, then it will be, the distance would be 0.5, then the perturbed trajectory will still continue to be a satisfaction, because if I can perturb it within that bound, still like all the points will be upper than the desired threshold. So as you see, for this type of formula, it would be the minimum distance. Now, let's say I have another signal, this green trajectory. And again, by visual inspection, we can say that this is also a satisfaction. But now the question is, which one is a better satisfaction? Both of them satisfies this formula. And now, like, this robustness degree can differentiate this, because if you look at the green trajectory, the minimum distance to the boundary is larger than this distance. So this means that this green trajectory can be subjected to more disturbances. And even if like it's under that amount of disturbance, it will stay to be a satisfaction. Now, if I change the formula to eventually, so this is a relaxer version. This time, I don't want all the time between 0 to 7, y has to be greater than 1. But it means that if I can find at least one point where y is greater than 1, that is like enough for me. So in the case of this eventually formula, then it would be the maximum distance. Because as you can imagine, if I perturb this trajectory like smaller than this amount, still I would be able to find at least one point that will be above the 1 threshold. So here, the motivation, like the reason that I show this to you is there is this robustness degree function, which is very crucial to quantify the degree of satisfaction. And the way that is calculated is based on the formula, whatever operators we see, we recursively use min and max functions. So that will bring us the mathematical expression of the robustness degree. So now, like if we want to formulate our learning problem with STL, let's say we have an MDP, just like the one I described in the beginning of the talk. So I have the set of states, actions, the transition function, and the reward function, but the transition function will be unknown, just like the standard RL problem. But the objective will be an STL. So how can we find a policy for this agent that will satisfy the desired STL formula? And we can actually pose two problems here. One is a standard problem, which is maximizing the probability of satisfaction. So this can also be described with standard languages. So this is the Boolean satisfaction. But with STL, we can also have an objective which would be maximizing the expected robustness degree. Because if we are maximizing the robustness degree, as you make it as high as possible, like if it is positive, then it will be a satisfaction. So this will also be a nice objective. If you can satisfy that spec, maximizing the robustness degree will take you a place where the robustness degree will be positive. Now, what are the challenges? So the standard formulation is in Q-learning. We learned that this is maximizing the expected sum of rewards. But with the STL, I actually described two problems with these objectives, probability of satisfaction, and then the expected robustness degree. So one problem here is, in the classical way, whenever you take an action, you see a reward, there's a consequence of it. And for that reason, in every time step, you just maximize the sum of rewards. But if you think about the right-hand side, like these formulations, I can calculate the satisfaction like after waiting for a while. For example, if I have a task as eventually go to A in 10 times step, and if the time is 3, I cannot make a decision whether this will be a satisfaction or violation. So I cannot calculate the Boolean satisfaction, and in the meantime, the robustness degree. So if you look at that, for these type of problems, we cannot directly use the Q-learning algorithm. The other thing is that there's also the history dependence. For example, in the standard Q-learning, wherever you are, if you remember, pi policy was described as a mapping from the state space to the action space. So wherever you are, you make a decision based on your current state. But in the case of these more complex objectives, your action selection may not necessarily depend only on your current state. For example, if you have a task as eventually visit A and then B, and let's think about a configuration where your robot is here in the blue triangle. If A is not visited in the history, then the optimal action would be following the green arrow so that it will take you to the region A, which will satisfy the first part of the formula. But let's say your robot is again in the blue triangle, but in the history, like it visited region A in the past. So this time the optimal action selection would be following the red arrow. So here, as you can see, if the robot is occupying the same state, the optimal action selection would depend on the state of the history of the states. So for that reason, again, the Q-learning will not be immediately applicable. So how do we come up, how do we handle these challenges? The way we do is, in order to incorporate the state history, what we say is that we augment the state space. For example, I said that we can create an MDP by discretizing the state space and action set, and then talk about this. But what if we create an MDP where each state is a partial trajectory? For example, I will say I will define a tau MDP, and here the tau state is mainly the current state and the most recent tau -1 state. So the current, the standard MDP would be 1 MDP because it only keeps the current state. But if I create a 2 MDP, then it will be the current state and the last state before the current state. In this illustration, you can see that if my agent is at sigma 1 state, then it can be in one of these 4 states in the 2 MDP. But the 2 MDP can differentiate. I'm at sigma 1, but previously I was at sigma 4. Or previously I was at sigma 3, sigma 1 or sigma 2. So there is this type of a differentiation. But with that, we would be able to bring up the history to the state space. So the history dependence can mainly be resolved with this augmentation of the state space by creating the tau MDP, where you are creating this tau state space, and all the others would be very similar. Now, the other problem is, if you look at the objective function, it's not in the form of sum of rewards. So we have this either robustness degree or the probability of satisfaction, and both of them are min-max functions or the recursive min-max functions. So I just want to show here is that the original robustness degree would be, as I said, this maximizing something. If in the case of eventually formula, or if it's a globally formula, it would be minimum of something. And if I want to, let's say, maximize the robustness degree, then I'm trying to maximize the maximum of something or maximize the minimum of something. Now, in the literature, there's this really nice approximation of the maximum function. which is this log sum x approximation. And a maximum function can be approximated by this expression. And the nice thing about this is there's also the theoretical bounds on how good this expression approximates the maximum function. And as you see here, the approximation is always an over approximation. So it's lower bounded by the actual max. And then there might be this amount of over approximation bound. But if you choose these parameters properly, then this approximation can be as close as to the maximum function. And what we do here is, if you look at this is the original formula, like formulation, the maximizing the maximum of something. So what I do is mainly I'm using this approximation so that instead of writing this maximum function, I'm just writing the approximate version of it. But if you look at this, now all of a sudden in my objective, I can see a sum of reward form, so over the time steps. And if you look at this, then I can actually calculate an immediate reward, even if I have an STL formula. So this is the way, by approximating the robustness degree, I can actually create the formulation that is like very suitable to the like standard formulation. Now we also have some theoretical guarantees. So like I'll just like describe it in a nutshell. The original problem would be an objective with min-max functions. And what I showed you in the previous slide is I use this approximation idea, and then I converted the objective into a sum of reward form. So this is the like approximate formula. And for this problem, we can actually use Q-learning immediately, because you have like you don't have the state in the like state is dependency, like state history dependency, and also you also fix the objective issue, like it's in the like standard form. So this problem can indeed be solved with the Q-learning. But we cannot stop here, because by using this Q-learning, you can find the optimal policy of the approximate problem. Now the question is, if I want to use this policy in my original problem, how good it will behave? Will it indeed, because it is finding the optimal policy of the approximate objective. And we also have a guarantee showing that the performance of the approximate policy, so here you can see it as pi star 2a, and then pi star 2 would be the optimal policy of the original problem. Then these can be related with this expression, and this is mainly derived from the from this, like the derivation of that portion is mainly coming from this approximate performance. So if we just use this, the performance of the optimal policy of the approximate formulation would be further away from the optimal policy of the original formulation, that amount. And which will tell us that if I choose my beta as large as possible, I can decay this part. And then again, the gamma is the discount factor. So if I just increase it, again, there's a way of like making this as small as possible so that they can get closer to each other. But one problem is that if my beta is really large, then it will influence the convergence rate. So that is something related with the learning. So we have some simulation results for this. And with that, we have this MDP where the transitions are like stochastic transitions is the agent can take an action to north, but there's the possibility that it can also follow one of these red arrows with small probability, but we don't know the actual probability distribution of that, with how many probability it follows the blue arrow or the red arrows. And the specification is a periodic behavior through this globally eventually formula. So this is in every 2-time step, go to A and go to B throughout emission of 14 time steps. And let's say region A is 3, region B is C. And for the time DP construction, this selection of tau is not arbitrary. So we look at the formula and make a decision about that. So if I say in every 2 times step, go to A, then I would need at least a 2 times step of history in order to make a decision about whether A is visited in the last 2 times steps or not. So for that reason, we look at the horizon of the inner formula, which is 2, and then we calculate our the tau value as horizon plus 1. So this means that I need to keep my current state and then the last 2 states. So for that reason, it would be a 3MDP case. And if we just run our algorithm over this 3MDP with the approximate formulation, what we see is after 1700 episodes, you see this periodic behavior. So this is indeed like going in between A and B. And after we stop these learning, when we calculate the quality of the policy, we observe that expected robustness degree is 0.422, and the probability of satisfaction is 0.936. So with that, I can just summarize that now, like, we have a reinforcement learning formulation that can actually work with signal temporal logic objectives. And I showed that through this log-sum approximation and the augmentation of the state space, we can achieve this goal. Now, one question is, what about the scalability of the learning? Because the problem with the previous methodology is that I said that we have to create this tau MDP, and tau MDP is mainly augmenting the state space in a way that I have to keep my current state and in the last tau minus 1 time steps. So if you think about a specification like in every 5 seconds, I want to visit this region, then you need to keep the last 5 seconds. But if my mission is like in every 45 minutes, I want to visit this region, then you really need to have a very huge state space that captures all possible state histories in the last 45 minutes, and which would, you know, explode the state space. So that would be a problem. So alternatively, we come up with another augmentation of the state space. And this is based on some flags. So this time, I don't need to explicitly keep the state history, but I'm going to define some flags, and those flags will tell me something about the tau last step history. And I have some illustrations here. So let's say I have a formula like globally eventually region A, meaning that we visit region A in every 10 seconds along a mission horizon of 16 times 60 seconds. And since I have one sub-formula here, I will only create one flag, and that flag will mainly keep track whether, like, in the last 10 seconds, region A has been visited or not. So what I will do is I will keep my current state and the current flag, and that's it. With these 2 variables, I can actually make a decision. And the way that we define this flag is, for example, in the case of that formula, you look at all of these last 10 time step history. And when you look at this, all these colored trajectories are a separate tau state, because tau state is mainly keeping the current state and the last tau minus 1 state. So all of them would be a separate state. But now with the flag MDP, what we do is that among these states, there's a commonality here. So all of these trajectories end up at this point when time is equal to 20. And the last time region A was visited is 3 times step before. So like the last time all of these trajectories visited was this point. Now what we do is, instead of expressing them separately as a separate state, we just merge them together. All the trajectories, like all the states here, would be S20, which is my state at time 20. and 0.7 flag, meaning that I have visited the region A the last time 3 times step before. Like the last time region A visited was like 3 times step before. So with that, means it's visited in the current time step. If flag is 0.9, it means that the last time A visited was t minus 1. And for 0.7, I already said that it is t minus 3. So if I'm at 20, it means that the last time I visited region A is 17. So with that idea, you can see that I can actually reduce the state space. So instead of creating a tau state for all possible elements, now this flag idea can give me merging these tau states together so that I can create a more compact state space. And yes, so each F state corresponds to multiple tau states. And if we just run some simulation case studies, what we see is that, so this is again one scenario, and we run every learning for 10,000 episodes, and we repeated this for 75 times, and we tested tau MDP and flag MDP. And what you see is that in the case of these empirical results, with tau MDP, we couldn't converge, like actually we couldn't find a nice policy after the end of 10,000 episodes. Because of this, you see this blue bar that is like here, very close to 0. But with the flag MDP, you see some distribution. So even like after 10,000 episodes, it was possible to find some reasonable policy. But I also want to note that this doesn't mean that tau MDP cannot find the optimal policy. This means that because of it has a larger state space, it will require more number of episodes, maybe 1 million episodes or 1 billion episodes, while flag MDP can come up with a reasonable policy with 100,000 episodes. So that is the difference between them because of the state space reduction. Now, is flag MDP everything? So does it solve everything? The question is no. For example, if you have a specification where there are a lot of possibilities, for example, I want to periodically visit A and B or C and D and E. So if you have multiple options, then we need to create a flag for multiple options. So for example, if you have a formula like in every 2 times seconds, I want to go to phi 1, phi 2, or phi 3, or maybe phi 100, then with tau state, you can actually describe, you can calculate something with these 3 elements, because this would require that I need to keep the current state and the last 2 times step. But the flag state would be the current state and 100 flags. So this time, like in the case of this, flag MDP would have a larger representation. So this shows that constructing a compact space that includes all the necessary information is very, very crucial for RL problems. And today I just show you 2 approaches. One has some benefits in some cases, the other one has other benefits in some cases, but those techniques do not solve the ultimate problem. Maybe one can come up with another idea which can behave better than these in some scenarios. So overall, in today's talk, I just show you how we can formulate these RL problems in the case of temporal logic objectives so that we can find these control policies. So before ending my talk, I just want to say a few things about my most recent research. So now, more recently, I'm considering reinforcement learning problems where there are some constraints that need to be achieved throughout the learning. So what I mean by that is, in the previous case, we said that the agent can actually choose any actions during exploration, and it observes the consequences, and these consequences can be a negative reinforcement or a positive reinforcement. But if you have, let's say, a safety constraint, and you don't want the system to be in an unsafe state, we don't have the luxury about exploring random actions and seeing something catastrophic, and then later on saying that, okay, I shouldn't do this action. So for that reason, under reinforcement learning, the domain constraint reinforcement learning is also becoming very, very popular. So there are like different techniques where people are incorporating constraints into the learning. For example, prior knowledge can be used. If I know that a portion of the state space is violating the constraint, then I don't want agent to explore that area. So this reduces the time spent to find the optimal policy under that constraint. But these type of techniques do not have theoretical guarantees. And the other thing is that we can penalize the violations. For example, in the case that I showed, instead of it's a temporal logic objective, if it was a temporal logic constraint, then we can also find policies that will not violate those specifications. But the thing is that the policy will be eventually learned. So in the beginning, there is still a possibility of violation. So you can violate your constraints. And some other techniques are, there is this very popular approach in control theory, which is called control barrier functions. So you can incorporate CBF into the learning, but CBF is like Lyapunov functions. So it will be like for simple safety specifications, you know how to define your control barrier functions, but if things get more complicated, it may not be very straightforward to define the CBF. So that would like have that type of a challenge. And finally, there is this shielding idea. So if you have some partial information about how the system can behave, then in any time step, this shielding mechanism might block the unsafe actions throughout the learning. For example, based on its exploration, maybe it wants to go in one direction, but after taking this direction, if there is a likelihood of constraint violation, shielding can block that action and make it to choose another action. And for this constraint RL part, my research is motivated by multi-use of autonomous systems. And what I mean by that is, as you can imagine, recently we are having these drones that can be used in multiple missions. And let's say this is a pickup and delivery drone. So the ultimate goal would be going to the pickup region and then delivery region. But in order to achieve that, it already has all of its sensors to collect some information. For example, I can also use this drone to, survey the environment and get some information. So normally, like, it can do this pickup and delivery, but how can I make it, for example, to explore the environment and, let's say, monitor some important region to increase situational awareness, but in the meantime, achieve the pickup and delivery task? So in that case, the primary task would be the constraint to the system. So no matter what, I want the system to achieve its primary task. But in the meantime, it would be great to look at the environment and find the high reward regions. So if you think about that, that would be mainly a constrained RL problem. So the classical one is just maximizing the expected sum of rewards. But the constrained one is, suppose that we have the same objective, but in every episode of the learning, I want to achieve this probabilistic constraint. And this is mainly, I want my trajectory, like in every episode, my trajectory should be one of the feasible trajectories. I define it based on S phi. So the probability of my trajectory to be in the feasible set should always be greater than or equal to PI desired. And I can also choose the PI desired. If I make it really large, then I enforce the specification in a very strong way. If it is small, then I give more freedom to the agent to violate the spec, but in the meantime, explore the area to collect the reward. And this is an illustration. So here we have a drone. Maybe I should just stop it. So we have a drone. It started from the base, and we just mimic green is the pickup, blue is the delivery. No matter what, it has to do this pickup and delivery mission, I guess, with a probability of greater than 0.9. And then these brown regions are no-fly zones, and there is a high reward region, which is this purple area, that is not initially known to the drone. So what we want to see is, while this drone achieves this pickup and delivery, it has to explore the environment in a very strategic way and then learn, for example, this purple region. And what you see is that in the beginning, it doesn't know about the purple region. So it goes to pickup and delivery and then look at the adjacent cells. But if we wait for a while, then it actually figures out there's a high reward region here. So now, as you see here, it spends some time in purple region, but it still continues to explore the environment. But while it does this exploration, we see the periodic behavior. It always does the pickup and delivery. And now, like after some time, it realizes that it is the only high reward region. So it spends its time in the high reward region, but again, achieves the pickup and delivery task. So with that, we can show that when you have a complex constraint such as this, like with some orderings, we can enforce the system to achieve it throughout the learning. So overall, temporal logics are, as you see, rich specification languages, and I use these temporal logics in the reinforcement learning domain. The standard reinforcement learning is through sum of rewards, but in this talk, I just showed you that how we can design rewards in a way that we can ensure the learning of the complex tasks. And again, overall, like I'm very interested in bringing these complex objectives and constraints into the learning problem. Here, like we are using Q-learning, but I am also interested in other like learning algorithms and how to provide formal guarantees with these learning algorithms. So with that, if you have any questions, I will be happy to answer. So this will be the end of my talk.